Yeah, good job, guys. Reading week's almost here. Only one day left for you guys tomorrow, and then you guys can finally relax, which is great. I think that at this point in the semester, a rest would be quite nice. And I got more good news for you guys. Assignment 8, which we're going to be covering in this seminar, it's a pretty easy assignment. Not too bad at all. I think that you guys will have no trouble with it. And as you guys will see, the seminar itself, because the assignment is pretty easy, the seminar is rather short, so you guys should be able to finish early and then have some time just to relax, which is great. All right, so let's begin with seminar number 8, which focuses on assignment number 8. So the seminar is going to be 4 questions, and the questions are pretty simple and straightforward. Looking at question number 1, it says a linear elastic isotropic material with the shear modulus G of 20 MPa and a bulk modulus K of 15 MPa is stretched such that the small strain matrix is given by, and we're given our nice 3x3 strain tensor, very reminiscent of all those questions that we dealt with a couple weeks ago. And the question wants us to determine 3 things. The first one is the strain energy stored during deformation, and as you guys have seen, this will be a very common question throughout all 4 of the questions. But part B and part C are a little bit different, where it says it wants the deviatoric strain energy stored during deformation. And finally, part C is the volumetric strain energy stored during deformation. So if you guys remember a little while back, we talked about stresses and how a stress tensor can be decomposed into a deviatoric stress tensor as well as a volumetric stress tensor. And the same principles are going to be applied here. As you guys will see, it's going to be a piece of cake. It's not going to be too bad at all. So the first thing in this question that's a little bit different than all the other questions that you guys have seen is we are not given the elastic modulus E or the Poisson's ratio nu. This question instead gives us the shear modulus G and the bulk modulus K. And as you guys are going to see, this is going to be a problem later on. So the question is, well, how can I get the elastic modulus or the Young's modulus E and the Poisson's ratio nu from G and K? Well, if we look at the formulas, it's actually pretty simple. Looking at the shear modulus G, we can see that it's a function of both the Young modulus E as well as the Poisson ratio nu, where it's simply equal to E divided by 2 multiplied by 1 plus nu. Moving on to the bulk modulus K, it's the same thing, where it's going to be a function of the elastic modulus E as well as the Poisson's ratio nu, where it's equal to E divided by 3 multiplied 1 minus 2 nu. But if we take a step back and look at this a little bit further, we can say, all right, well, I have 2 equations here with 2 unknowns. The unknowns being the elastic modulus E as well as the Poisson's ratio nu. Well, if I have 2 equations with 2 unknowns, I know I can solve for those 2 unknowns. So from these 2 formulas, we can easily solve for the Young's modulus E and the Poisson's ratio nu. And moving forward, you guys are going to see why we have to do this. So let's look at question A, or part A of the question. It wants the strain energy density, the formula for it. Well, we know that for a linear elastic isotropic material, and yeah, it's kind of a mouthful to say, but that's a very important piece of information, we can find that strain energy density function, which is that big U with the bar up top. It's equal to 1/2 of the summation of sigma ij multiplied by epsilon ij. And you guys are going to hold up, Clayton. I don't want to deal with summations. Those aren't fun. Can we expand this out into one simple formula? Well, the answer is yes, where the strain energy density can be as follows, where it's equal to 1/2 of sigma 11 multiplied by epsilon 11 plus sigma 22 times epsilon 22, etc., etc. So as we can see here, we explore all 6 terms of both the strain tensor and the stress tensor. So there's kind of be the big piece of information we need is we need both the strain tensor and the stress tensor. So if we take a step back and say, all right, well, what are we given in the question? Well, we're given that strain tensor. So therefore, all of the epsilon ij's and gamma ij's in this formula, we're good to go. We know all of them. The problem is going to be, what are those stress components? Sigma 11, sigma 22, sigma 33, etc. So this is going to be the only real piece of information we're going to have to solve for in order to calculate the answer for part A. However, luckily for us, we have that nice relationship for a linear elastic isotropic material, where the stresses, or the stress vector, can be found by taking the elasticity tensor, or I guess the elasticity tensor that applies to this situation, which in this case is a linear elastic isotropic material, and then we multiply that by our strain vector. So if we look at the right-hand side here, the elasticity tensor first, Well, after we solve for the Young's modulus E, as well as the Poisson's ratio nu, we have everything we need to have in that elasticity tensor. It's not going to be a problem at all. If we look at the very right-hand side, we have that strain vector. Now we're given the strain tensor, so we can easily calculate that strain tensor. So therefore, everything on the right-hand side of this equation, we know it's good to go. We can solve for those stress components. And of course, once we know those stress components, all we have to do is substitute it into the formula on the previous page. We have our answer for part A. So it's a little bit of work, mainly that we have to deal with this 6x6 tensor, but other than that, it's pretty straightforward. It's just basically plug and chug your way to the answer. So that's going to be part A. Now, if we look at part B, it's a little bit different, where it says, all right, well, we have that strain energy, but what about the deviatoric strain energy? Well, in general, there's a nice formula for that deviatoric strain energy, where the deviatoric strain energy is simply the von Mises stress squared divided by 6g. What is g? Well, that's that shear modulus, and luckily for us, that question gives us that shear modulus, so therefore g, that's not going to be a problem. The only thing that we have left is that von Mises stress. So we remember that we have that nice big formula for the von Mises stress, and we can calculate it if we know all the stress components. Now, if we look at the question right from the beginning, we don't have those stress components. So that'll be an issue initially. However, luckily for us, in part A there, we had to calculate those stress components to solve for part A. So by the time you guys get to question B, we actually already have those stress components. So it's basically substituting them into the von Mises stress equation to find that von Mises stress, and then substitute it into the formula above to find the deviatoric strain energy. So as you guys will see, this is not a problem at all, because basically once we get to part B, we'll have all the information we need to directly solve this problem. So you say, all right, well, that's great. How about part C, where it wants that volumetric strain energy? So at this point in the question, we have two ways to calculate the volumetric strain energy. The first one, which I coined the traditional way, because this will work no matter what your situation, is we have a nice formula for that volumetric strain energy, which is simplified into that P squared, where P is that volumetric stress divided by 2K. So if we look at this, we say, all right, well, K, that's not a problem at all. We're given K in the question. That's the bulk modulus. All we need is that P squared. How do I find it? Well, P is simply the trace of our strain tensor. So sigma 1, plus sigma 2, plus sigma 3, all divided by 3. So just like before, this would be a problem if we did not have the stress components. However, after part A, we have sigma 1, we have sigma 2, we have sigma 3. We can just plug and chug our way to the answer. Now, there is a second way to calculate it because we have solved for part A and part B at this point. So this is what I call the quick way. So let's recall that the strain energy is actually the sum of the deviatoric and the volumetric strain energy. What does that mean? It means that we have this nice relationship down here. And if we look at the components, the component on the left-hand side, that strain energy, well, we solved for that in part A. We know what that is. How about the deviatoric strain energy? Well, we solved for that in part B. So if we look at this equation, we actually only have one unknown, which is that volumetric strain energy. So if we wanted to, all we have to do is take our answer from part A, subtract our answer from part B, we're good to go. So this is a nice little relationship that we can use. Now personally, what I like to do, I would do it the traditional way, get an answer, and then I would use the relationship down below to simply check my answer. If I do part A, B, and C, and I compare it and that equality doesn't work out, well then you know something went wrong along the way. Now, a nice part of this formula is it doesn't always have to be solving for the volumetric strain energy. Let's say that I had the strain energy from part A and I had the volumetric strain energy from part C, well then I can simply solve for the deviatoric strain energy, something like that. So it's a nice way to switch between one strain energy to the other rather simply. So this is going to be part C, and with that the question will be done. So that concludes question number 1. Is there any questions concerning question number 1? Everybody's happy so far. Good, good, good. That's what I like to see. Hopefully it remains that way. So question number 2, I'm going to be honest with you guys. This is going to be the hardest question for you guys out of the assignment. But as you guys are going to see, it's heavily reliant on what we did in assignment 7. So if you guys have really good Mathematica code for assignment number 7, well, then question number 2 is actually going to be just a simple extension of what you guys did. So question number 2 says the shown beams below have a length L, Young's modulus E, moments of inertia I, and are subjected to a constant distributed load Q. I didn't have the pictures of the beams, but the two beams are exactly what you guys had in assignment 7, where one beam is simply supported, so it has pins on both ends, while the other beam down below has two fixed ends. So it's just those two boundary conditions. And the question wants us to determine 3 different things. The first one is the total strain energy of the simply supported beam, and part B is the total strain energy of the fixed ends beam. And what you guys are going to see, this is going to be the main part of the question. If you guys solve part A and part B, well, then you're basically good to go, because if we look at part C, it says it wants the ratio of the total strain energy of the simply supported beam to the fixed ends beam. So all we have to do is take our answer from part A and divide it by part B. We're good to go. So again, the main thing is going to be, what is the total strain energy of a beam? All right, well, let's look at that. As we know, the total strain energy can be calculated as the integral of that strain energy density function over the volume. And first thing I like to say is over the volume, well, that kind of sucks. I don't like integrating over a volume. I like integrating over lengths. So what we can do, oops, kind of press back, we can simplify this formula as a triple integral. And all I'm doing is I'm integrating with respect to all the dimensions of the beam. So if we look at the first integral on the very left-hand side from 0 to b, well, I'm just integrating over the thickness of that beam, that in-plane thickness, or that x3 direction. My integral in the middle, I'm integrating from negative h over 2 to h over 2. Well, as we know, that's the height of the beam, so I'm just integrating over the height of the beam. And then finally, our integral on the most right-hand side from 0 to L, well, I'm integrating over the length of the beam, so in the x1 direction. Now, what's nice for you guys is, as this is parametric, all we have to do is substitute b, h, and L into our integrals. We don't really have to worry about defining them. So the main question is going to be, all right, well, this integral I can just throw into Mathematica. It's not going to be a problem. However, I need to figure out what that strain energy density function U is. If I don't have that, well, then what am I supposed to integrate? So the main goal of this question, finding out what U is. Now, just like before, we have a linear elastic isotropic material, so we have that nice big long equation for it. Now, unlike the previous question, it gets a little bit simpler. And the reason why is because there's a lot of simplification, because we know that sigma 22 is equal to sigma 13, which is equal to sigma 23, which is equal to sigma 33, which is all equal to 0 for Euler-Bernoulli beams. What does that do to our equation? Well, it gets rid of 4 of those terms. So now we have an actually much simpler equation where that strain energy density function U can be found as simply 1/2 sigma 11 multiplied by epsilon 11 plus sigma 12 multiplied by gamma 12. So we look at this from a step back, we can say, all right, well, the only thing that we need are those 4 components, the 2 stress components, sigma 11, sigma 12, and the 2 strain components, epsilon 11, gamma 12. But that's simply 2 multiplied by epsilon 12. So as we can see, 4 components, and then this question will be solved. So the question becomes, how do we get those 4 components? Well, let's start with the stress components. And as you guys may remember from assignment 7, we actually solved for those stress components. At the end of assignment 7, at the end of question 1 and question 2, you had those stress functions for the beam. So you guys already know how to do this, but we'll do a quick little recap. The first thing that we need in these type of beam questions when we're trying to solve for stress components is going to be that deflection function. Well, how do we find that deflection equation y? Well, we use our nice little relationship where EI multiplied by the 4th derivative of that deflection equation is equal to the distributed load Q. Now, we're given EI, or we're not explicitly given the values, but we know that our answer is going to be in terms of EI, so that's good. And we have a Q, so that's good. The only thing in this equation that we don't have, of course, is that deflection function. However, in Mathematica, as you guys have already done, we can use the dsolve command to figure out what that deflection function is going to be. Now, we can take that a step further and we say, all right, well, if we have that deflection function or that deflection equation, well, then we can find the shear and bending moment functions, because the shear function V is simply going to be that EI multiplied by the 3rd derivative of that deflection function, which we solved for above. Similarly, that moment function is going to be EI multiplied by that second derivative of that deflection function. So again, if we have that deflection function, we can find both the shear and the bending moment functions. And you guys may have forgotten assignment 7, you say, all right, hold on, Clayton, why do we need those? Well, if we look at the stress components, sigma 1,1 and sigma 1,2, they have very nice formulas. And as you guys will see in the formulas, they're going to be dependent on those functions. So if we look at stress component sigma 1,1, it's simply -1 multiplied by that moment function. So this is why we need the moment function, multiplied by x2, where x2 is simply going to be x2, and then divided by the moment of inertia I. Now, as the question said, our answer is going to be in terms of that moment of inertia I. That's not going to be a problem. The only real unknown we have here is that moment function, which is why we solve for it. If we move on to stress components sigma 1,2, or that shear stress component, we know that there's a nice relationship where sigma 1,2 is equal to -1 multiplied by that shear function multiplied by Q divided by I times B. Now, if we look at this equation, we say, all right, well, we solve for that shear function, which is why we needed to. The only thing that we don't really know is going to be Q. However, if our axis runs through the centroid, or sorry, I should be more specific, our x1 axis runs through the centroid of the beam, we have a nice formula for Q in terms of H and in terms of B. So as you guys are going to see, this is not going to be a problem at all. So if we take a step back and we look at this, we say, well, our two stress components, I have two nice equations for them. All I need to do to solve for these two components is find my moment function and find my shear function. How do I do that? Well, they're simply calculated from that deflection function. So that's not going to be a problem at all. Again, this is just a straight repeat of assignment number 7. So if you guys have Mathematica code, you guys will actually already have these functions ready to go. The thing that's a little bit different than assignment 7 is we didn't talk about the strain components in beams. So remember that in assignment 7 we asked for the stress components, but we didn't ask for those strain components. So how do we figure out those? Well, what's nice for us is if we ignore Poisson's ratio and assume small deformations at the same time, the displacement function can be expressed simply as u is equal to -x2 multiplied by the first derivative of the deflection function for u1. U2 is simply going to be our deflection function y, and U3 is going to be 0. Well, why is this nice? Because if I look at U here, and I already have that deflection function, well then I already have my displacement function, because the only unknown here is going to be that deflection function y, but at the same time, I already solved for y, so I'm good to go. Well, what's nice about this is because if we have that displacement function, as we've talked about so many times before, we can find the displacement gradient. Why is that important? Because with the displacement gradient, we can find that small strain tensor. And of course, that small strain tensor, those will have all of our strain components that we need. So if we have our displacement function u, we can simply find the displacement gradient using this big long formula, but luckily for us, it simplifies quite nicely. Now what we can do is we can say, all right, well, we have our displacement gradient. How do I find my small strain tensor? Well, there's a nice formula where the small strain tensor is simply 1/2 multiplied by the displacement gradient plus the transpose of the displacement gradient. And what does that give us? That gives us the following, where epsilon 1,1 here is going to be equal to -x2 multiplied by the second derivative of that deflection function, which is great because if we look at this, x2 is just x2, it's no big deal, but that deflection function y, that's our only unknown, and we know what that is, so we're good to go. If we look at the other strain component that we needed, epsilon 1,2, well, we see that it's actually 0. So if epsilon 1,2 is 0, well, then we actually didn't need the stress component, sigma 1,2, because it's going to cancel out. So now that we have all these components, what we can do is we can simplify that equation we had before. So remember that currently we had this equation, and we had 4 unknowns that we're trying to solve for, sigma 1,1, epsilon 1,1, sigma 1,2, and gamma 1,2. But now what's nice for us is that we can expand it out. We say, all right, well, hold on. Epsilon 1,2 is 0, so gamma 1,2 is 0. So all that stuff on the very right, that kind of goes away. So therefore, our strain energy of a beam can simply be found by taking 1/2 of sigma 1,1 multiplied by epsilon 1,1, which is the following. So if we look at this equation, this is going to be how we're going to solve for these. And the only thing that we have in these that are going to change between part A and part B is going to be the boundary conditions. Now keep in mind for a simply supported beam, those will have different boundary conditions than a fixed end beam. What happens when we change those boundary conditions? Well, we change the deflection function. And of course, if we change that, then we're also changing the moment function. So if we look at the strain energy formula here, we see that we both have an M and we have a Y. So if we change those boundary conditions and we change M and Y, our strain energy, of course, will be different for both the simply supported beam as well as a fixed end beam. And then again, part C, well, we're just taking our answer in part A, dividing it by our answer in part B. So that's going to be how you guys do the question. Again, if you guys have good Mathematica code from assignment 7, which I've seen it all looks great, you guys will be good to go. And this will be the hardest question of the assignment, in my opinion. So what do you guys think? Is there any questions concerning question number 2, or do you think it's pretty straightforward? Good for me. All right. Awesome. So that's great to hear. If you guys are going to question number 2, then the rest is going to be a piece of cake. So let's move on to question number 3. Question number 3 is a little bit different, but it's actually pretty simple. So it says for a linear elastic isotropic material, so again, the same material as questions 2 and question 1, it says with a Young's modulus E and a Poisson's ratio nu, express the strain energy density function under the condition of plane stress. So that's going to be key here, that plane stress, in terms of part A, sigma 1, 1, sigma 2, 2, and sigma 1, 2. So basically, part A wants that whole strain energy density function in terms of the stress components. And then part B says epsilon 1, 1, epsilon 2, 2, and gamma 1, 2. So part B is basically saying we want that strain energy density function as a function of the strain components. All right, well, that doesn't sound too bad. Let's move forward. Well, we know, just like questions 1 and 2, our strain energy density is that nice long formula. However, this question is very nice because it says we have a plane stress condition. What does that mean? Well, it means that sigma 1, 3 is equal to sigma 2, 3, which is equal to sigma 3, 3, which is going to be equal to 0. So what can I do to that equation? I can cancel out 3 terms, and then I'm actually given the following equation, where our strain energy density is going to simply be 1/2 sigma 1, 1 multiplied by epsilon 1, 1 plus sigma 2, 2 times epsilon 2, 2 plus sigma 1, 2 times gamma 1, 2. All right, so all we're going to have to do here now is express this equation in terms of only the stress components for part A, and then for part B, only the strain components. So if we look for part A here, the only problem that we actually have in this is going to be those strain components epsilon 1, 1, epsilon 2, 2, and gamma 1, 2. Because again, we don't want strain components for part A. We want this all in terms of those stress components, as well as the Young's modulus E and the Poisson's ratio nu. In part B, we do the opposite, where we say, all right, well, our strain components are fine, but we're going to have to actually replace all of those stress components in terms of strain components, as well as the elastic modulus E and the Poisson's ratio nu. So how do we do this? Well, we know that we have that plane stress relationship, which is really great because not only did it cancel out a bunch of terms in our strain energy, it also gives us a very nice relationship between the stresses and the strains. So let's say I know the stresses and I want to find the corresponding strains. Well, we have the nice relationship above. And vice versa, if I know the strains but want to find the stresses, well, we can manipulate the equation above to get the following. So if we look at this, this is great because for part A, we're going to use the first relationship. Because if we solve that right-hand side, what we'll do is we'll get a nice equation which says, all right, well, my epsilon 1 is going to be equal to something times sigma 1, 1. So we can actually convert all of those strain components to stress components, which is what we want for part A. The second equation, or the second relationship below, we can use that for part B. Because what we can do is we can find out what all of our stress components are in terms of strain components, and then substitute them into that equation above. So this equation's actually, this question itself is not too bad. All we're going to have to do is find a relationship between the stresses and the strains, or vice versa, and substitute them into that equation that we had for the strain energy density. So that's question number 3. It should be pretty straightforward, but do you guys have any questions about question number 3? I'll take it as you guys are pretty good, which makes me happy. We'll go on to question number 4. So question number 4 is kind of a tricky question because it looks really complicated, but it's actually quite simple, as you guys will see. So question number 4 says, consider the Hogestad material model for concrete in compression that follows the following nonlinear relationship between the uniaxial stress sigma 11 and the uniaxial strain epsilon 11. So this is a very popular material model for concrete. As you guys will see, it's kind of a parabolic curve here. Parabolic curve, that's what we're dealing with. And one of the things I just want to mention, this is for concrete in compression. Not concrete in tension, just concrete in compression. And as you guys will see, nice parabolic relationship. It's going to be a little bit funky, but not too bad. And we're given the equation for it, which is great. As we can see in this equation, we have our sigma 11, our uniaxial stress, is equal to F prime C. And this is where you guys, hold on. What's that, Clayton? I don't know what that is. Well, F prime C is the peak compressive strength of the concrete. So if I have a concrete cylinder and I crush it under a press, it's going to have that peak stress. That's what F prime C is. Multiplied by 2 times epsilon 11 divided by epsilon naught. Again, you guys are going to say, hold on, Clayton. I know what epsilon 11 is. That's my uniaxial strain. But what is epsilon naught? Well, that is the peak strain corresponding to that peak compressive stress. So again, if I crush the cylinder, I'm going to have a nice stress strain curve, and that location of the maximum stress, the strain that occurs at, that is epsilon naught. Now it says, if the peak compressive stress of the concrete is 22 MPa, so that's going to be our F prime C, which occurs at a strain of 0.002, which is going to be our epsilon naught, and the concrete crushes at a strain of 0.0035, it wants us to solve for 5 different things. The first one says, plot the relationship between the stress and the strain if the concrete crushes when the strain reaches a value of 0.0035. Well, as you guys will see, question number A, that's a piece of cake. Because we have our equation, all we have to do is plot it. Not too bad, pretty straightforward. One other little fun fact that I'm going to say is that strain value of 0.0035, if you guys actually take concrete design, this is actually what the code book says concrete crushes at. So this is a very set in stone value. I believe for all of your guys' assignments, even though they're randomized, it should be 0.0035 for every single one. Now, part B and part C is where things get a little bit different. Part B says find the strain energy stored when the concrete reaches peak load. And part C says determine the total strain energy dissipated when the concrete fails by crushing. So the questions sound very similar where we're dealing with that strain energy. But there is a difference between part B and part C if we look at the wording, where part B says strain energy stored and part C says strain energy dissipated. So that's going to be a question I'm going to ask you guys a little bit later. Why are we saying stored in part B, and why are we saying dissipated in part C? So I want you guys to kind of ponder that as we move forward. Moving on to part D, it says determine the compressive stress at which the concrete fails. Well, that's easy. All we have to do is substitute that strain value at which it crushes, and the equation will give us the corresponding stress. So part D, easiest question you guys can find. And finally, part E says find the ratio between the compressive stress at which the concrete fails by crushing and the peak compressive stress. So all we have to do is take our answer from part D divided by the peak compressive stress. We're good to go. So if we're looking at this this question, the only 2 things that might give you guys troubles is going to be part B and part C, where it deals with that strain energy. Part A, part D, and part E, well, all we're doing is just using that equation that we had before, nothing too complex. So let's talk about strain energy. Up until this point, in the previous 3 questions, we always use the same formula for strain energy, where U is equal to 1/2 multiplied by sigma 11 times epsilon 1 plus etc, etc, etc. Now what's nice for us is we have a uniaxial case. Therefore, sigma 11 is our only non-zero component. What does that do for us? Well, that gets rid of 5 of the terms. So basically, our strain energy density is simply 1/2 multiplied by sigma 11 multiplied by epsilon 11. You say, all right, well, that doesn't sound too bad. I can say that my strain energy is equal to sigma 11 times epsilon 1 divided by 2, and we're given a nice formula for sigma 11. So I can substitute that formula for sigma 11 to get the following long equation. And as we can see, there's going to be 3 different parameters in this equation: f prime c, epsilon 1, and epsilon naught. Well, we know what those constants f prime c and epsilon naught are, so the only real unknown is epsilon 1. So all we have to do for part B and part C is substitute our value of epsilon 1 as the peak strain or the crushing strain to get our strain energy, right? Well, the answer is actually going to be no. Please don't do this. This is not how you deal with one of these questions. Now, I'm going to ask you guys in the chat for those juicy participation marks. Why is this not the correct approach? If this is the same approach that we did for part A, or sorry, question 1, 2, and 3, why is this no longer the correct approach for question number 4? Anybody brave? All right, well, I'll let it go. You guys just wrote a midterm, so I'll let you guys get off easy. The correct response is because this is a nonlinear material. So if we look at question 1, 2, and 3, it says very clearly that for a linear elastic isotropic material, but the key there was linear. Now, if we look at the concrete model, as I mentioned, it's actually a parabolic shape. It's not a linear shape. So since this is a nonlinear material, things are going to change a bit. And you guys are going to ask me, all right, well, how exactly does it change? Well, let's look at linear behavior. As we know, if we were to plot the stress strain curve, it's a nice straight linear line. Nothing too crazy about it. However, when we plot this concrete model, you guys will see that it has a parabolic shape, which we deem as a nonlinear behavior. How does this play into our current question? Well, if we remember the strain energy, what that essentially is the area under those curves. So the way to calculate strain energy for linear and nonlinear is the exact same. However, our formulas that we had in the notes as well as the theory, those were all tailored for linear behavior. There was nice simplifications. Because if we look at the area under the curve for a linear behavior, well, it's simply a triangle. So therefore, our strain energy is going to be 1/2 multiplied by sigma 1 multiplied by epsilon 1. And that's why all of our formulas had those 1/2. It's because of the linearity of the system. Now, when we get to nonlinear behavior, we're doing the same thing where our strain energy is going to be the area under that curve. However, that curve is in a triangle. You don't really know what that curve is going to be. So how do we find the area under the curve? Well, we're actually going to have to integrate. So what we're doing for these type of nonlinear questions is our strain energy is going to be the integral of our stress function with respect to the strain. So in this particular case, we're going to integrate that sigma 1 function that we have with respect to epsilon 1. Now, the key that's going to change in part B, it says it wants that peak strain. So what we're going to do is we're going to integrate from 0 all the way until that peak strain. Part C says it wants until the crushing strain. So we're going to integrate from 0 all the way into that crushing strain. However, the methodology to solve part B and part C is going to be the exact same, where we're using this nice little integral to solve for it. The only thing that's going to be different is our integral limits. And that's going to be it for question number 4. So before we end question number 4, I asked you guys a question. I said, how come when we're integrating from 0 to the peak strain, we say that the strain energy is stored? Now, if we consider the strain energy when the material crushes, why are we saying that the energy is dissipated instead of stored? What do you guys think?
Is it because when the material fails, there's still some material intact, so some is lost, but there also is some still technically stored inside the material?
You're on the right track. And the answer is when something breaks, the energy is released. It's not stored anymore. It's released in the terms of sound or the actual permanent strain, stuff like that. So you're right. When the concrete crushes, the material is released. The energy is released. If we don't fail the material, it's still under all that stress. Therefore, it's storing the strain energy. So Hopefully that makes sense to you guys. Again, it's not something that's really a part of the course. It's more just a little fun fact. Now, I want to go explore another little fun fact for the bonus marks for you guys. And my first question to you guys can be, how many of you guys have taken either Civi 374 or 474 or even 479, the design courses for structural engineering? Have any of you guys explored those yet? No, no one has. Oh, so someone's taking 374. So as you guys are going to see when we do design of structures. So if we're designing, let's say, a steel moment frame building, or if we're designing a concrete shear wall, it doesn't really matter. What you guys will see is that in design, we never really use energy. If we're dealing with the ultimate moment capacity, well, then we're concerned with the yield strength of steel or the peak strength of concrete. Or if we're dealing with serviceability, so deflections, we're basically dealing with how stiff the material is. So energy is never really considered in design. So I'm going to ask you guys, is there a scenario in design where energy is important? Because let's be honest, we do a lot of research into the energy of materials. You guys are taking it in this course, and in my own research, I've dealt with it a lot. So why is energy important in design if we never really see it in typical design? These are hard questions, so don't be afraid to just say whatever is on your mind. Again, this is just for fun. It's a fun fact. All right, no one's quite brave. Well, I'll tell you this. Energy is actually very important in seismic design, ductility-based design. And you guys are going to say, Clayton, well, sounds important, but how is it important? Well, this is going to scare a lot of people. It scared me at first. If we look at the loads imposed on a building by an earthquake, so that's what seismic design is, earthquake design. What we'll see is that at the base of the structure, there is going to be, let's say, 3,000 kilonewtons of shear. 3,000 kilonewtons. That's a ton of kilonewtons. So what do you guys think? If we're designing a building for 3,000 kilonewtons, do you think that we can easily design a building to withstand 3,000 kilonewtons? What do you guys think? If you guys remember from your design classes, typical values of shear are 200 kilonewtons, maybe 300 kilonewtons, but not 3,000. So Johnson says no. Any other takers? Do you think it's easy to design for 3,000 kilonewtons? Yeah, so everyone's saying no, and that's the correct answer. So this is what's going to start scaring people. In earthquake design, an earthquake imposes 3,000 kilonewtons. We don't design the structure to withstand 3,000 kilonewtons. We design it so that it can dissipate the energy of the earthquake. And that has to do with a nice factor. So if I'm in a design scenario and I figure out that my earthquake's putting 3,000 kilonewtons, what I would actually do is I would design the building for 769 kilonewtons. Does that scare you guys? If I know that my loads are going to be 3,000 and I'm only designing for about 770 kilonewtons, do you guys want to be on an earthquake in a building when an earthquake is getting hit? Probably not. Oh, Denzel says, yep. Well, I'm sure it'd be quite the experience. I'm not sure if you guys had Dr. Yong Lee, but apparently when he was in California and an earthquake hit, he told me he lay on the ground so he can feel it shaking. Now, me personally, I would run out of the building. When I was in Chile studying earthquakes, I was scared every night that an earthquake was going to hit. I was always so prepared. But that's off topic. Going back into the design, what you see is what we do in earthquake design is we take our earthquake load, which is 3,000, and we divide it by an RD factor. Now, the D here stands for ductility. So what happens is we see how the structure dissipates energy, and from the amount of energy the structure is able to dissipate, we get this RD factor. Now, for typical, let's say a concrete shear wall or a masonry shear wall, it's usually around a value of 3, so we can take that earthquake load and divide it by 3. So Denzel talks about the midterms. And Johnson says, wouldn't the building have something like shock pistons? I'm not too sure what you were referring to there, Johnson. Maybe you can show me a picture or send me an email asking. There is a lot of research going into how to mitigate the effects of earthquakes, but in the end, what that would do is if we can soften the earthquake, well, then we're able to increase this RD factor. So this RD factor comes directly from energy, and that RD factor is actually what allows us to design for earthquakes. Because if you try and design a building for 3,000 kilonewtons, those walls would be at least 1 meter thick and 10 meters long and full of steel, and they would just be a nightmare. So this is why we use energy in design. It's for earthquake design. More specifically is how can we lower those earthquake loads? And that's it for the seminar. Because again, this last part, just a little fun fact for your benefit only. It's not actually for the course material. So is there any questions about question number 4 or earthquake design even? How did ancient civilizations design for earthquake? That's a great question. So if you look at ancient structures, let's say the pyramid, look at how thick those bricks are. They are huge, and that's the reason why they're so big, is because the depth of the brick allows it to have that strength. Now, if I were to take our normal masonry, which is usually about 20 centimeters deep, and I didn't put any steel, just like the ancients did, and I were to put it in an earthquake zone, it would fall over in a second. And they realized that. So what they did is they made those blocks extremely huge. So if I were to design, let's say, a building, and I made that building the size of a pyramid, well, then of course that building is not going to fall down because it's so beefy. The problem is if I were to go to an architect and show them that design for the building and say, yeah, my walls are 2 meters thick of pure concrete, oh, they wouldn't be too happy with you. You'd get you get fired right away. A good example of this would actually, even if you go to the Edmonton Legislature building, you look at those old buildings from the early 1910s, notice how big those bricks are. That's how they compensated for their lack of strength, was they just built it so huge. Any other questions? No? You guys have any fun plans for reading week? Study, catch up? Oh, Johnson also says for taller buildings, how did they prevent shear from traveling up the tower? So actually, if you guys study shear in tall buildings, the opposite happens. Where if a building is hit by an earthquake, the maximum shear actually increases as you go down the building. So at the top of buildings, there actually is very little shear. It's basically just the bottom of the building that you're worried about. Because if you think about an earthquake, it's moving the ground back and forth. So it's basically a building is just a giant cantilever beam. So that's where all those maximum loads are going to be, is at the base there. That's why if we're also testing a shear wall in the lab, what we'll do is we'll build the shear wall for the first story of the structure, test that, and we say, all right, well, if this one's good to go, then the shear for the rest of the building, of course, will also be good to go as well.